to develop. The survival adaptations developed by these final populations exceeded anything previously documented in the fossil record. Some populations developed the ability to survive in volcanic regions by processing toxic gases and extreme heat that would have been instantly lethal to normal dinosaurs. Others adapted to polar conditions by developing antifreeze proteins and specialized metabolic processes that allowed function at temperatures approaching absolute biological limits. Forest-dwelling populations developed enhanced immune systems and detoxification capabilities that allowed survival in environments poisoned by atmospheric toxins. Volcanic Refugia provided protection through geothermal energy that maintained habitable temperatures during the impact winter period. These populations developed respiratory modifications that allowed them to process volcanic gases and extract oxygen from chemically altered atmospheres. Bone chemistry analysis shows that volcanic Refugia dinosaurs consumed mineral-rich volcanic ash and developed specialized digestive systems that could extract nutrients from previously inedible materials. The geothermal environments provided stable temperatures that buffered against the extreme climate fluctuations that eliminated populations in other regions. Polar Refugia populations survived by developing unprecedented cold weather adaptations that allowed function in sub-zero temperatures for extended periods. These populations modified their cardiovascular systems to prevent freezing damage and developed specialized fat storage systems that provided energy during extended periods of reduced activity. The polar dinosaurs developed behavioral adaptations that included group huddling and shared body heat conservation techniques that maximized survival during the darkest periods of the impact winter. Evidence shows that these populations created insulated shelters using available materials and maintained social structures that enhanced group survival. Deep forest refugia provided protection through dense vegetation that filtered atmospheric toxins and maintained local climate stability. These populations developed arboreal adaptations that allowed them to exploit vertical forest resources and avoid ground-level environmental hazards. Forest-dwelling dinosaurs modified their dietary patterns to consume tree bark, roots, and other forest materials that provided nutrition when normal food sources disappeared. The dense forest canopy created microenvironments with stable temperatures and humidity levels that buffered against the extreme climate changes affecting open areas. These refugia maintained dinosaur life for thousands of years through carefully balanced ecosystems that maximized resource utilization and minimized environmental stress. The populations developed sophisticated resource management strategies that included seasonal migration within refugia areas and coordinated breeding programs that maintained genetic diversity within small populations. Evidence shows that refugia populations established sustainable hunting and foraging patterns that prevented overexploitation of limited resources while maintaining population stability over extended periods. Hybrid species emerged from desperate survival attempts as isolated populations faced genetic bottlenecks that threatened their continued existence. These hybrid forms represent evolutionary experiments that occurred as populations adapted to extreme conditions and limited genetic diversity. Fossil evidence shows species that combined characteristics from different dinosaur lineages, creating forms that possessed enhanced survival capabilities but reduced reproductive success. The hybrid populations represent the final evolutionary attempts of dinosaur species to adapt to impossible environmental conditions. The gradual decline of refugia populations occurred as environmental pressures continued to intensify over thousands of years. Each refugia faced unique challenges that eventually overwhelmed even the most remarkable survival adaptations. Volcanic refugia populations succumbed to increasing toxicity levels that exceeded their detoxification capabilities. Polar populations faced extending periods of darkness and cold that depleted their energy reserves beyond recovery. Forest refugia populations experienced resource depletion as vegetation communities collapsed under continued environmental stress. Evidence of the very last dinosaur individuals provides a poignant picture of their final struggles against impossible odds. These specimens show signs of extreme nutritional stress and desperate attempts to survive on increasingly inadequate food sources. Bone chemistry analysis reveals that the final individuals consumed previously inedible materials and survived on minimal nutrition for extended periods before succumbing to starvation and environmental toxins. The last dinosaurs show evidence of continued social cooperation and parental care, even under the most desperate circumstances. The final Refugia populations came remarkably close to surviving the extinction event entirely. Some populations persisted for over 3,000 years after the main extinction, demonstrating that dinosaur survival was not impossible but rather dependent on access to specific environmental conditions and resources. The evidence suggests that if environmental conditions had stabilized even slightly sooner, some Refugia populations might have survived to recolonize areas where conditions improved. These final populations represent the ultimate testament to dinosaur resilience and adaptability in the face of impossible environmental challenges. Their survival for thousands of years after the main extinction demonstrates that these creatures possessed remarkable evolutionary flexibility and determination. Yet the story of which creatures ultimately survived the extinction reveals patterns that challenge everything scientists thought they knew about evolutionary success. The fossil record reveals that survival depended on specific biological traits rather than evolutionary dominance or physical strength. Small mammals, birds, crocodiles, turtles, and certain marine organisms persisted through the environmental catastrophe, while the mighty dinosaurs disappeared entirely. These survivors possessed precise combinations of characteristics that proved essential for enduring the prolonged chaos that followed the asteroid impact. Body size emerged as the most critical factor determining survival chances during the extinction crisis. Creatures weighing less than 25 kilograms had significantly higher survival rates than larger organisms because they required fewer resources and could exploit smaller food sources that remained available during environmental collapse. Small mammals survived by consuming seeds, roots, and insects that persisted in underground environments protected from surface devastation. These creatures could maintain stable populations on resource quantities that would have been insufficient to support single large dinosaurs. Metabolic efficiency separated survivors from victims through energy conservation capabilities that proved essential during resource scarcity. Creatures with lower metabolic rates required less food and could survive extended periods without regular feeding, while high metabolism dinosaurs faced starvation when food sources disappeared. Cold-blooded reptiles like crocodiles and turtles survived by reducing their activity levels and entering dormant states that minimized energy expenditure. Their metabolic flexibility allowed survival on occasional feeding that would have been impossible for warm-blooded dinosaurs with constant energy requirements. Dietary flexibility determines survival through the ability to process different food sources as environmental conditions changed. Omnivorous creatures survived by switching between plant and animal matter as availability fluctuated, while specialized feeders faced extinction when their preferred food sources disappeared. Small mammals consumed seeds, nuts, and roots that remained buried in soil during the impact winter, providing reliable nutrition when surface vegetation died. Birds survived by eating seeds and small prey that persisted in protected microenvironments, while large herbivorous dinosaurs starved when plant communities collapsed. Behavioral adaptability became more crucial than physical adaptations for surviving the rapidly changing post-impact environment. Creatures that could modify their behavior patterns, feeding strategies, and habitat preferences survived by adapting to new environmental conditions. Small mammals demonstrated remarkable behavioral plasticity by exploiting new ecological niches and adjusting their activity patterns to avoid environmental dangers. Birds modified their migration routes and nesting behaviors to cope with altered climate patterns and food availability. The ability to exploit underground environments provided crucial protection from surface environmental devastation. Burrowing mammals survived by accessing resources and maintaining stable temperatures in subterranean refuges that protected them from atmospheric toxins and temperature extremes. These underground habitats contained food sources including roots, fungi, and invertebrates that remained available when surface ecosystems collapsed. Soil environments provided insulation that maintained habitable temperatures during the impact winter when surface temperatures dropped to lethal levels. Aquatic environments offered protection that allowed certain species to survive through environmental changes that eliminated terrestrial populations. Freshwater environments maintained more stable conditions than terrestrial habitats and contained food sources that persisted through the crisis period. Crocodiles and turtles survived in aquatic refuges that provided thermal stability and access to fish, amphibians, and plant matter that remained available when terrestrial food sources disappeared. These aquatic survivors could also exploit both water and land resources as environmental conditions changed. Some species survived by completely transforming their ecological roles and exploiting opportunities created by the extinction of dominant species. Small mammals expanded into ecological niches previously occupied by dinosaurs, developing new feeding strategies and habitat preferences that allowed exploitation of available resources. These ecological role changes occurred rapidly as survivors adapted to fill vacant niches in post-extinction ecosystems. The transformation process involved behavioral modifications that allowed exploitation of new food sources and habitat types. Reproductive strategies played crucial roles in determining which species persisted through the extinction crisis. Species with rapid reproductive cycles could replace population losses more quickly than those with slower breeding rates. Small mammals with short generation times could adapt genetically to changing environmental conditions through natural selection, operating over dozens of generations during the crisis period. Species with extended parental care and complex social structures faced greater challenges maintaining population stability under extreme environmental stress. The geographic distribution of survival showed that certain regions provided better refugia than others for different types of organisms. High-latitude regions offered some protection from the worst effects of atmospheric disruption, while tropical areas provided thermal stability that benefited cold-blooded survivors. Coastal regions offered access to both terrestrial and marine resources that enhanced survival opportunities. The variation in regional survival rates demonstrates that extinction was not uniformly distributed, but rather created complex patterns of survival and death across different environments. These survival patterns inform our understanding of current extinction risks by revealing which biological traits provide resilience against environmental catastrophe. Species with small body sizes, flexible diets, and rapid reproductive rates show greater resistance to environmental change than large specialists with complex ecological requirements. The ability to exploit multiple habitat types and modify behavior patterns provides crucial advantages during periods of environmental instability. The lessons from prehistoric survival patterns apply directly to modern conservation strategies facing climate change and habitat destruction. Protecting small populations of adaptable species may be more effective than focusing solely on large charismatic species that require extensive resources. Maintaining habitat diversity and connectivity allows species to exploit multiple ecological niches and adapt to changing environmental conditions. Understanding which traits promote survival during environmental crises can guide conservation priorities and help predict which modern species are most likely to persist through current environmental challenges. These discoveries reveal that extinction events are not random cosmic accidents, but complex processes governed by specific biological principles. The patterns of survival and death during the dinosaur extinction demonstrate that evolutionary success depends on adaptability rather than dominance, flexibility rather than specialization. The research reveals that dinosaur extinction was not about evolutionary limits, but about scientific measurement errors that masked their true stability. Advanced occupancy modeling completed in 2025 demonstrates that a parent dinosaur declined before the asteroid impact resulted from sampling biases rather than actual population decreases. Fossil collection patterns created artificial scarcity that suggested dinosaurs were already failing when they were actually maintaining stable populations across diverse environments. These discoveries fundamentally change how we understand mass extinction events and their underlying causes. The complexity of dinosaur survival strategies shows that traditional extinction models failed to account for sampling limitations that distorted our understanding of prehistoric population dynamics. New modeling approaches reveal we must reconsider mass extinction drivers and sampling biases to accurately interpret